Are we good with the recording? Okay. Jake will tell us about using WebAssembly as an intermediate language for proving all the things and software sandboxing.
Thanks, Jonathan. Right, so this is joint work with Ben Lim and Brian Pardo. First off, what is WebAssembly? Or before we even get there, why is WebAssembly? So there have been multiple attempts to provide safe, native-like performance for web applications. From the academic world, it's been NACL, and there's been all the others, and they've all failed, and it's still JavaScript. Yeah, and this is terrible. This is unfortunate, because JavaScript is not great for reasoning about performance, for reasoning about security, especially because it's a high-level language, and these are, like, performance and security matters at the lower levels as well. You have to reason through the interpreters that are running the code, the multiple JITs. Each browser implements their own JIT, and some browsers have multiple JITs. There's a garbage collector that messes with the predictability of your performance. So thus, WASM was born. It's supposed to be a saner target for compilation, and mostly because it's made to be closer to real hardware. So now we can get to what is WASM. It's a virtual architecture that makes it portable. It's a stack-based design, which means it's simple. That's what the code looks like. It's actually structured code, which means you don't really have the nice structure you want, like if-then or while loops. Since it's close to real hardware, it is fast. Having no garbage collector, unlike the JVM, for example, means that you get predictable performance. And it has a really basic type system, which means you get some safety, but it's kind of lightweight. So like, you see the I64 const 1 or I64 sub. I64 sub says it must subtract two 64-bit integers. It has a really succinct and well-defined semantics. This really facilitates analysis. It makes it much easier to write analyses on it as well. In short, basically WASM can give you lightweight, safe, and fast execution of untrusted code. But this construct is much more general. You'd probably want that even beyond the web. And basically, since that's super useful, this comes into play whenever you're executing untrusted, unsafe, or complex, unverified code. Generally, if you have an unsafe program and you have some safe API that you want it to interact with and you want to interact with it through, and you don't want it to mess with much in the environment, your environment might actually be in the same address space within the same process. You could do this. For example, you have plugins. There are programs that require extensions. In this, you don't want to crash in the plugin to mess with your application. CDNs have recently started taking this up. So content delivery networks are used to speed up accesses on the web by moving static content closer to the end users. But a lot of the web is dynamic. So CDNs are like, if you give us WASM code, we might execute this for you closer to the users.
Which is today's keynote, right?
Yeah. Missed it. My bad. Okay, so basically it extends to this idea of edge computing and like smart card, bunch of other places where you need sandboxing, basically. And like this is a well-studied thing again. It has a rich and long tradition since it's a generic construct, but there have always been these technological and marketplace hurdles to adoption. Some solutions require compiling from source. Some say that the initial code should not have undefined behavior. Some require complex binary rewriting. Some solutions are supported only by one vendor, and a whole bunch of other issues. So what we propose is WASM is an attractive narrow waist for providing this generic construct of safe sandboxing. Basically, yeah, for all the reasons I mentioned earlier, we can actually use it as by providing a verified sandboxing compiler from WASM to be able to execute code in a safe way. The other advantage is lots of compilers have shown up from various languages to WASM, and basically we believe it's at a critical mass of users. This is ongoing work. We're working on building a formally verified sandboxing compiler, and so I'll be talking a bit about our early design decisions, some challenges we've been facing, and some surprising insights we've gained along the way. First off, a formal definition of sandboxing. It's written slightly more informally than the previous talks, especially since this is closer to the end of the day. Let M be a partial map representing memory, where the domain is the actual sandbox. If a program tries to read or write outside of that domain of it has access to in memory, it's said to violate it. Quite simple. If a program never does that, it's safe. And a compiler is safe if all programs it generates are safely sandboxed. Basically, we want the following signature written in sudo f star for people who read that. If you have an initial state, for all possible initial states, the resultant program in the target language should evaluate safely. So how does this compare to traditional compiler correctness, basically semantic equivalence or semantic preservation? In that, you usually start off with, if you give me a safe input program, then I'll give you back an equivalent safe output program. But if you give me an unsafe input program, I say nothing. Or even worse, if it's a malicious input program, it could say nothing, but it could be worse. On the other hand, what Provably-Safe sandboxing says is we hope to give you back an equivalent program, but we're sure it's going to be safe. Even in the case of unsafe behavior in the source language, even in the case of maliciously written programs. We believe this is an orthogonal and different thing from standard compiler correctness. So as part of building this compiler, our choice of semantics, we chose small step semantics rather than big step with traces. Even though, like earlier, I wrote the f-star thing in with a single eval over the entire thing. Well, this allows us for direct reasoning at each program point, and also allows us to reason about infinitely running programs, which for cases like CDNs, you might be running infinitely long, so servers and such. We originally started off with big step because it led to a very convenient and nice definition. But unfortunately, we found it quite difficult to write proofs about this because of the structure of certain things. And also, it can't handle infinitely running things well. The other surprising thing we found was that, at least earlier on, unstructured seems to be nicer than structured. Now, naively, WASM has structured code. It would be nice to maintain the structure, if then else, while loops. We've known since way back that gotos are considered harmful. But the problem with WASM is it has break n and continue n, with n being a runtime value at times. What are these? These are the same as break or continue in C, except they mean jump out n levels in your loop. So you jump out of n loops directly, and what this leads to is a lot of non-trivial corner cases as you're reasoning about each of these bits of code. Currently what we do is very, very early on, as part of the compiler, we move over to an unstructured IL, which basically is control flow graph based, and so just contains jumps and branches.
Sorry, before you go, it's very hard to interpret this. What does your source language look like? Oh, you're coming to that?
It's WASM. WebAssembly is the
Oh, you're
input.
trying to compile it?
Right, it's from WebAssembly to machine code.
Aha. Okay.
So we get the input to our compiler is WebAssembly code. Yes. As part of these unstructured ILs, we have multiple similar ILs throughout our compiler. This allows us to easily add and remove instructions. So WASM, as I mentioned, is a typed language, and this means we can actually hold on to a lot more information earlier on, and thus we actually introduce and remove instructions along the way to hold on to additional data that we need to lose as we approach actually closer to native code. For example, we have a high-ret instruction that can also keep track of which program locations it's allowed to return to. It'll make sense soon as to why we need to hold on to that. But holding on to multiple similar CFG ILs allows us to reduce duplication within the semantics of modeling each of these languages, and also allows us to reuse optimizations and analyses. We have a single generic data flow analysis framework, since we use just a common syntax across all of them. And the semantics, there's a lot of commonality that we can factor out. We have proven termination, for example, in that. So as far as the sandboxes themselves go, given the way WASM is, a single large sandbox turns out to be insufficient. This is because WASM has indirect function calls, it has imports, it has globals, it has a bunch of things where they need to be held separate from the main memory that you have access to. However, the way WASM is structured allows for like a surprisingly clean handling of this, and we can elide basically all runtime checks except for the main memory accesses. WASM has a single large linear memory called the memory with its current version of the standard. They do, however, say they may expand that in future versions. Now, again, based on our use case of fixed locations insufficient, but that's easily handled, just making everything register relative. So overall, sandbox sizes are arbitrary but decided at compile time, and locations are decided at runtime. For handling function calls, direct calls are handled directly, as you'd expect. But indirect function calls, WASM holds on to expected types for each function call that you do. So we store a single function table and just do a single lookup within that. This also allows us to check whether the function we're calling is of the right type. And since this table exists outside of the main memory sandbox, this table cannot be tampered with. Which brings us to the notion of CFI. Control flow integrity is necessary for getting this provably-safe sandboxing. So when we need to talk about CFI, we have to talk about what the potentials are for failures within this. So one, as I mentioned, is indirect function calls. We keep the lookup tables outside of the main sandbox. And indirect jumps kept outside thing. We also make sure that the indices are checked at runtime to be within bounds before the jump or the call respectively, thereby guaranteeing CFI, which is a necessary part of proving the sandboxing. So our current implementation, it's in progress. As I mentioned earlier, we take WASM as input. We currently output x86-64 code with plans to extend to other targets, for example, ARM. We've been building this in F-star, which is an ML-like verification-oriented language. As you saw, everparse, for example, is built in F-star. It supports SMT-based automated reasoning, which turns out to be extremely helpful for building this sort of compiler. And our machine models, the x64 model is inspired by Veil, which is a part of Project Everest. Again, written in F star. So Veil is used for verifying high-performance cryptographic code. And WASM, we kind of are inspired very heavily by the reference official spec written in OCaml. So as far as the structure of the compiler goes, we take in input as WASM code, parse it, and destructure it, again, very early on, in fact using everparse, to convert it quickly into CFG IL. In fact, to bring it to the family of CFG ILs. Then there's multiple phases for compilation and optimization, which stay within the CFG IL family. Following which, there's a specialization pass that makes it x86-64. And the sandboxing happens as the last phase of this. And finally, we have printing, which gives us .s file. Of course, then it is assembled and linked. Our machine models are all written in F star using Z3, which leads to a TCP that looks like that. In particular, basically, we do not need to trust anything that gave us the WASM. By that, we just need to trust the printing and our machine models, and of course the spec for safe sandboxing. As far as future work goes, we currently do a very conservative elision of the runtime checks. We plan to extend it further using more analyses based on abstract interpretation. There are some enriched versions of WASM, like MS WASM, which extends WASM to hold on to some information from the C++ level, some pointer information and such. We believe this may help us elide even more checks. And we also want to see how this interacts with preserving other properties such as correctness and side channel resistance. Side channel resistance being necessary if you're using this for cryptography, which is a common use case for running WASM. So in summary, we believe WASM is a great narrow waist for providing sandboxing for the reasons I've mentioned at the top. This gives us a very useful generic construct that we can use in a lot of use cases, and it's orthogonal to compiler correctness. There's many surprising insights we've gained along the way, and there's a non-trivial design space for exploration here. And using a family of unstructured CFG-based attacks with just the semantics deciding to drop or hold on to certain instructions is an extremely useful thing we found. Thank you.
Oh, sorry, if there's anybody else. Not next year. Well, go ahead. So, okay. Of your TCP, I'm trying to understand. So you're actually proving that the x86, you're only proving the sandboxing problem, right?
Yes.
Well, like, I see, okay. So like, really, like, your optimizations could be busted, but it doesn't matter as long
Yes.
No, but they are also instrumenting right at the end, right?
Sorry?
They are instrumenting after the optimization, right?
Right. So as Tayan mentioned, the optimizations could be busted. That's fine. Yes.
So you don't have functional correctness, it's just about...
Currently, we don't have fully proven functional correctness. We're working towards it.
Okay, so that's a goal.
It is a goal, and in fact has led to some of the design choices along the way.
Good.
Sorry, I have a very silly question, which is probably related to this. I actually don't understand what you are trying to sandbox. I mean, so this is just one module.
Right.
You are just trying to make sure that it does not, for example, corrupt your tables. What exactly is your sandboxing? Or what's the check that you insert?
Okay.
What's
So,
the
so,
bounce
so
rate?
basically, the WASM code that we get is a single module
Yeah.
which exports and imports functions
Yes.
to be used with the
Yeah.
environment.
Yeah.
And basically, what we're sandboxing is that none of the memory accesses
Yeah.
it does
Yeah.
can actually do anything else.
So
In some sense.
it doesn't
So
corrupt the metadata.
it doesn't corrupt the metadata. It
Yeah.
does not corrupt any other memory within the process,
Yeah,
because
okay.
you're going to take this
Sure. Okay.
module
Yeah.
and write it.
Now I understand. So in the last step, where you actually do the instrumentation of these instructions, right?
Mhm.
For the sandboxing, so you literally take every indirect read and write,
Right.
and you instrument it.
That was what we used to do.
Okay.
Turns out, using the analyses that we have, you can actually prove that a bunch of these can be elided
And this analysis is entirely at the assembly level.
at the assembly level. Again, I should probably jump back to right. So basically, the specialization phase
Yeah.
is almost trivial. Turns out the x86 model also is practically the same as that CFGIL. And what that means is that our data flow analysis framework still applies on top of the x86 side, which means we can apply verified data flow analyses on top and figure out where to elide these checks safely.
Okay. Thank you. Yeah.
Sure.
I guess that was my next question. So like that analysis is actually verified.
Is verified. We have proof for it, yes.
Okay, great.
Theorem, right? That your x86, 64 code per the machine semantics will not touch
Right.
memory outside of its allocated space.
Yes.
One last question while Marco sets up. Yes.
Curious if your IL has any relation to, I feel like the non-verified compilers for WASM also have CFG-based ILs. Is yours similar? Is it different?
I'm sorry, I'm not sure I understood the question.
There are like non-verified compilers,
Right.
and they also use controllable graph ILs, like Greenland.
Right. So
and is yours similar? Is it different?
Uh,
The design decisions that you made that were like, oh, what they did didn't make any sense. And I'm just curious.
right. So in fact, some of our decisions have been inspired by some of these other compilers. So I believe V8 uses what they call the CF nodes approach, which is a combination of a CFG-based and data flow graph-based thing in a single huge graph C, yeah, they too tend to go unstructured quite early. But yeah, other compilers I'm not quite sure. I should.
Right. Let's thank the speaker again.